Hello, TC-CoE Summit participants. This is Gernot from the seL4 Foundation and Trustworthy Systems at UNSW Sydney. It's a shame I couldn't join you in person, so this is a recorded talk, which I will have to do. I'll be giving a brief update on what's been happening in the seL4 Foundation land, and then I spend some time on the research we're doing at Trustworthy Systems. So, Foundation update. I'll keep this brief as it was all covered in the recent AGM of the foundation and also much of it at the summit. So the outstanding event of the past year was definitely the fourth seL4 Summit, the first one ran by the seL4 Foundation, which took place in Munich in October last year. It was an awesome success. We had a sellout crowd. The room was full to the last seat. We had a few members participating remotely as well. We had keynotes, talks, discussions, experience reports, overviews, ask me anything, sessions, panels, and training and tutorials. And we had industry sponsors. Some were not able to join because of travel restrictions, etc. But truly, the event had a buzz I haven't experienced for years, and it was really awesome. And we're looking forward to the next summit, which will be the fifth summit that will be held in Minneapolis in 19 to 21 September. So we're going back to the US. We had a call for proposals out, and that closed a week or so ago. And we received a high number of proposals, even more than last year. And the program committee, which you see here, the faces on this slide, are working hard in reviewing those. And we expect an announcement on around the 22nd of May of the preliminary program. So that's the summit, and beyond that, there's been a few things that have been happening, so I'll give a brief update on this news. So previously, we had a really tumultuous year where the Trustworthy Systems group separated from CSIRO and set up at UNSW and went through, honestly speaking, a near-death experience, but that's all behind us. We now had a year of consolidation where things are running relatively smoothly and stably. So the highlights were that we have now the seL4 trademark registered in both US and China, and we got a bunch of new members on board, a few departures as well, but some of the new members are really exciting. Obviously, Google is a well-known name. We have the UK National Cybersecurity Centre. So this is a government organization that demonstrates their support for the seL4 technology by being a member, but also funding a lot of our ongoing activities. So this is really awesome. And another non-profit joining is the AutoWare Foundation. That's been fairly recent. And this is an indication of the level of interest in the autonomous driving community. AutoWare is an autonomous driving kit specifically for cars. We've been working a lot on improving community support. Part of that was an overhaul of the endorsement scheme, which is now just focused on services rather than products. And we are making strategic investments in community support, including providing seed funding for some projects from foundation funds, but generally providing explicit support through people hired by the foundation or contracted by the foundation to provide support for users. And this seems to be going well so far. There's been some technical progress as well. That's mostly in the domain of the technical steering committee. So we have a new kernel fastpath approved for notification signaling, which is really critical for some of the work I'll be talking about later, and VM exceptions, so to enhance performance of virtual machines on top of seL4. There's ongoing work funded from various sources on verifying the mixed criticality version of the kernel and the kernel for the 64-bit ARM platforms, and I'm not sure what my keyboard is doing here. That is all done by Proofcraft, and we have ongoing work directly funded by the foundation on providing stable Rust support for seL4, which is, of course, there's a big demand for that in the community, and a number of new platforms have been supported. So that's a very brief wrap up of news at the foundation front. And I almost forgot the most exciting news of all, namely seL4 has won the 2022 ACM Software Systems Award. ACM is the largest and oldest professional organization of computer professionals, and its annual Software System Award recognizes a software system that had lasting impact either in real-world deployments or in conceptual advances. And in seL4's case, I think we can agree that it's really both of them. So that's great recognition for our system and its community of adopters, and the lots of hard work that went into seL4 over the years. So on behalf of the team, I would really like to thank everyone who contributed to that. Thank you. And now I'll talk about present research and development activities at the Trustworthy Systems group at UNSW. The real crucial development here has been the introduction of the seL4 core platform. That happened year before last, but it's really become matured and usable and the base of all our ongoing work in the past year. So everyone who's ever tried to deploy seL4 is painfully aware of the high barrier of uptake. It's a really complex system. It's got a very sophisticated API that's meant to support a really general systems and policies on top. And this generality, together with requirements of verification, has a cost in terms of usability. And for most of the systems people are building, this is not really required. People are mostly deploying seL4 in the embedded and cyber physical space, where you have much less general requirements. And the seL4 core platform is specifically designed to support these application domains in a way that makes the system much more approachable. So it's a very thin wrapper around seL4 abstraction, but designed in a way that essentially forces you to use seL4 correctly. This is something we've seen over and over, that people are really unsure on how to use the seL4 primitives to the best effect. And the seL4 core platform takes a lot of the guesswork out of it by just providing simple primitives that naturally map onto the right use patterns of seL4. And also it comes with a software development kit that really makes development straightforward. So you no longer have to mess with a complex kernel build system, but can use a kernel binary and develop around that using whatever development environment you prefer, whether it's Makefiles or CMake or something complex. So what are these abstractions of the core platform? There's very few of them. The one core abstraction is the protection domain. So this is the equivalent of a Linux process, although it's somewhat more restricted. And it has a number of entry points. One of them is the init function. Every protection domain has an init function. And this is what the system calls at system startup time to give each component, each protection domain, a chance to get into a defined state. And then the rest is left to the user. So there will be other protection domains. They can communicate. And the abstraction there is a communication channel. So a communication channel connects exactly two protection domains. And the main operation there is you can signal a communication channel. And if the blue domain here on the right signals that communication channel, then that will be translated into an invocation of the notified entry points in the target protection domain. And in that way, these protection domains can send asynchronous signals between each other to invoke operations. And to make that efficient, there's memory regions which you can map into one or more protection domains. So this is the way to provide shared memory communication. And between the shared memory of the memory regions and the signaling of communication channels, you have everything you need for doing basic communication. And there's one more thing, and that's protected procedure calls. So this is a proper mapping onto seL4 IPC in the way it's meant to be used, namely to execute a defined function in a different protection context. And so what a protected procedure call does, if the blue domain executes a protected procedure call on the channel, then that will invoke the protected entry point of the target domain. Protected entry points are optional, so only server kind of domains will provide them. But if they're provided and you have a channel to the PT, then you can invoke it and you can pass arguments. And that's the total set of abstractions of the core platform. It's very straightforward. And what it furthermore does is it prescribes a simple event-driven programming model. So that takes a lot of the complexity out of writing seL4-based code. So both the notified and the protected function, they're just straightforward functions that are not meant to block. In particular, the protected function is not meant to block, and that just execute in a sequential fashion. And when you're done, then the system basically goes back to waiting for the next notification or protected procedure call, but that's hidden under the hood of the core platform, which does everything for you. And importantly, the core platform guarantees that these three functions, the init, the notified, and the protected function, are executing atomically with respect to each other. So in a single core protection domain, you need no concurrency control whatsoever. Again, takes out a lot of complexity and allows a really simple way of programming seL4-based systems. Of course, with this dramatic reduction in complexity, can you really build what you need? Well, yes, you can. We've done a fair bit of work on providing an high-performance I/O system, starting with networking for seL4 systems based on this seL4 core platform. I'm not going to go into the details of this. This is sort of a symbolic representation of what we have. So we have a device driver model, and then we have a consumer at some stage. And they are, again, very lightweight. They communicate via simple, lock-free, bounded, single-produce, single-consumer queues. These are very easy to implement, again, taking complexity out of the system. And reducing everything to a bare minimum. The driver model that's prescribed here is extremely simplified compared to what you might be used in Linux. And all up, from these building blocks, we designed a really lightweight, extremely modular design for a networking system. It supports device sharing, so you have a device driver, and if you want to share the device, then you have a multiplexer component that multiplexes the device driver between the various clients, and all that with zero copy, highly asynchronous, straightforward code. A device driver, that's future work, that's work in progress, that's not done yet. You can have a driver VM that encapsulates a Linux driver if you want to reuse a legacy driver. So how does this compare, for example, to Linux? Well, it's worlds apart. So Linux, a network driver for the experimental platform we're using here, has 4,000 lines of code on its own, and the whole Linux networking system is about 1 million lines of code, hugely complex. In contrast, our design, which we call the KISS design, keep it simple, stupid, has a network driver that consists of 700 lines. This is for the same NIC. That network driver was written by a second-year student, a pretty good student, but a second-year student who has not written a program a year and a half before she wrote that driver. And that itself is a testament to how simple it is to write code for this environment. We have a multiplexer, we have copiers for security, etc. All up it ends up being a couple thousand lines compared to the million of lines of code of the Linux system. And we expect that we'll be able to dramatically simplify the IP stack as well. At the moment, we're using LWIP as a library linked against the client. And yeah, the approach should allow us to take complexity out of this driver as well. Okay, you'll say this is all really nice, but it's going to be really slow. Well, this is actually where the really good news comes. It's actually blindingly fast. So we did experiments with a gigabit Ethernet NIC on one of our embedded ARM platforms and compared it to Linux, and this is the result. So what you can see here is throughput. We apply a certain load varying between 100 megabits per second and a gigabit, and we measure the achieved throughput, so the packets that are actually being received and echoed back through the network. So the client is a simple echo server. And you can see two lines. The green is seL4 and the orange one is Linux. And you see expected linear increase as the load increases, the achieved throughput increases, except at about 700 megabit Linux plateaus, whereas seL4 throughput keeps on growing until we saturate the wire. Why does Linux not keep up? Well, we see that by looking at the CPU load on the system. This is all single core. And the dotted lines here are the CPU load. So in this case, smaller is better. And you can see the yellow Linux line is much higher than the green seL4 line. So Linux uses way more cycles to process the same amount of data. And eventually at about 700 megabits, it hits the 100% ceiling and therefore the performance plateaus, whereas seL4 keeps scaling. So performance is really very good. And the bottom line here is simplicity wins. It's not only good for correctness, it's actually good for performance as well. But speaking of correctness, we are obviously in the seL4 land and we like to prove things correct. Can we do this? Well, given the complexity of the system, a few hundred lines of code for most components, maybe that's possible, shouldn't it? Particularly given that the complexity of the code we have, the little code we have, is actually much reduced by this simple event-driven model. So can we have the source code and a specification and prove that the source code actually satisfies the spec? Well, we believe so, and we believe we can do this in a push-button fashion where we use SMT solvers to completely automatically provide proofs of code implementing its spec. And at the same time, we're also working on a better programming language for device drivers. You may remember hearing me talking about the Pancake language before, which is a C-like language that's got a well-defined semantics, unlike C. It's simplified in some respect, but importantly, it has a compiler that is proved to produce correct code. And this is something we expect to be able to use to verify drivers. So our aim for the next year or two is to have a verified network driver written in this Pancake language. And the cool thing is that we expect we can do a lot of this fully automatically. Why do I make this claim? Well, we actually have a really good indication because we worked on verifying the seL4 core platform itself. So remember this networking framework I was just discussing, this is all built on top of the seL4 core platform. And it, for example, it performs massively better than the previous Camkis-based systems we had. But now we actually also worked on verifying the core platform using these push-button techniques. So if you have a system that's built on top of the core platform, you have an SDF spec that stands for System Description Framework, formalism, whatever, I forgot, sorry. And that describes what the system looks like. So this is the equivalent of the Camkis ADL. And so it describes the components in the system, the protection domains, and obviously they are implemented in C. In the future, maybe Rust. At the moment, it's C. And then this gets linked against the seL4 core platform library to produce an executable system. And we verified two critical aspects of that. One is the seL4 CP library itself, and the other is the system initialization. So looking first at the core platform library, it is we specification of that library, of the functionality of that library, and then did proofs, SMT solver based push button proofs that the implementation is functionally correct as a refinement of the library specification. So in that sense, we verified the actual runtime part of the core platform. And on the initialization side, you may remember the CapDL formalism, which is used for describing low-level access rights in seL4. And we have a mapping of this SDF, the core platform specification, on this CapDL formalism. And we also have a proof of correctness of this mapping. And that allows us to reuse earlier verification artifacts, which were developed in the context of a DARPA case program, where we did generated a provably correct system initializer from the CapDL spec. At the moment, this linkage is not quite complete because the CapDL spec is all based on pre-MCS seL4, whereas the core platform is strongly tied to MCS. So the whole story will be complete only after the MCS kernel verification is complete, but we got the building blocks in place. And as I said, this was done largely with SMT solvers. And you will get a first release of this in a few weeks. So we're very close. We've basically finished the work and just cleaning it up. And this really gives me confidence that we can use these push button techniques on other bits of an seL4 based system that's based on the core platform, in particular bits and pieces of our driver framework. And we want to take that further as well. So the goal for the next few years, and at the moment we're looking at various sources of funding, is to build a complete operating system aimed at IoT and cyberphysical systems that's built on the seL4 core platform and around the principles we developed for the seL4 device driver framework. And then that will have not only networking, it will have file systems or persistent storage and the ability to transfer, to communicate or share data through the file system between components. And it will have some other things you need for complete OS, including the ability to restart or reload components, etc. Everything really built the same way we built this high performance networking system. So very fine-grained modularity with very strong separation of concerns. And when I mean strong separation of concerns, I'm really serious in the sense that every component has one and only one job. For example, in the I/O system, the device driver has one and only one job, and that's translating between a hardware-specific device interface and a hardware-independent device class interface. So the rest of the system can then interface to that. The multiplexer has one and only one job. Actually, there's two multiplexers, one for transmit and one for receive packets, and each one has one and only one job, which means for the receive, sending incoming packets that are received from the driver to the right client, and the transmit mux obviously has the opposite function of collecting packets from clients and sending them to the NIC. And where we need it for security, we have copy components that again have one and only one job, which is copying a packet. So it from the shared DMA space into the client address space. So this is the fine-grained modularity with strong separation of concerns. Beyond that, we're applying what I call the principle of radical simplicity, where we really think hard about what features do we really need and only provide those and nothing else, no gimmicks. And this extends to any policy we have in a system. And instead of doing the usual thing, which is, for example, what Linux does, is to try to have relatively universal general policies that adapt to different use cases, we take the radically opposite approach of saying, no, a policy module implements one and only one policy for your system at hand. But we make it simple enough so every engineer can change that policy by just rewriting this simple policy module, which again is going to be a few hundred lines of code, given a template provided, and write a new policy that represents your particular use case. So the whole idea is fairly consistently of the simplicity, doing everything to make things simple, and therefore also helping you people to really build systems on top seL4. Once we have a high performance device driver for a particular NIC, you can take this as a template and do a new one for another NIC. The multiplexer, there's going to be probably about 3 or so standard versions of that, because there's not that much policy you need there. Copy a module is, you really need just one for input and maybe one for output. So really simple templates that taken together give you a high performance system, but also allow you to adapt by just redoing components and plugging them in and out. And of course, the key thing of this is that it's performant, and we demonstrated already with networking that we can do it performant. If you can do networking, you can do everything else. Networking is the most performance critical part in an OS typically, but also make it verifiable. And this is why we're so extreme on simplicity, because the simplicity is what will enable the verification using these push button techniques. So we're looking at verifying individual components. We'll probably start with a multiplexer or a copier, using SMT solvers to verify them. And at the same time, we're working on using model checking to verify the communication between these components, because we took a lot of complexity out of the system completely, but we also shifted some complexity from the components into communication protocols, and they can be buggy. And we found that we didn't have sort of functional bugs, but we had a lot of performance bugs we were hunting down, and they were always in the communication not being done completely right. So we're working on using automated techniques, model checking, for fixing this. So this is going to keep us busy for a couple of years or so, but you will see the first signs of that coming out probably later this year. The device driver framework itself is already specified. Device drivers are available, or some of them, and we'll keep pushing this out. So this is where we are at the moment. There's lots of other stuff that are going on in research. In particular, our time protection work is progressing, but I don't really have time to go into all of that. So I'll leave you with this for now. Thanks to the awesome Trustworthy Systems team that's making this all possible. As you can see, we've grown to a decent size again, and we're actually growing further. There's a half dozen new people coming on board next month. So we'll be over 35 people in about a month's time. So there's a sizable group, and we can do great things. And I really hope that you keep on working with us, and in particular, help us develop the system by adopting what we do and refining it, using it in your deployments, etc. Thank you very much, and have fun at your summit.